Hello everyone, good evening. I am Siavash Rezazadeh, Director of Robotics, Locomotion and Control Lab at University of Denver. And this was the title that I proposed to this guy, Control Lab, a humanoid robot which has highly vectorable joints. But then, in the past few days, I kind of got the feeling that some of our colleagues look at us, the proponents of vector variability, as some sort of cult members. So I decided to change the title to So I consider myself a cult member, but no one told me about these things when I was working on the control of this robot. So I was kind of grumpy at other cult members. So just thought maybe I can share this with you, the problems that we faced through the control, so that if you are working with vector robots, you can use them. So this is Mitra, our humanoid robot that we have been working in the past 3 years or so at University of Denver. I showed the design last year, so just a quick overview of what we did. It was intended to be designed with roughly height, weight, joint range of motion, and length similar to humans, because we are interested in human locomotion. Also, we try to have mass distribution and inertias at this tangential plane similar to those of humans, which is kind of, I guess, different from what is popular now in community, using very light legs, because obviously it simplifies the control to a great extent. So we purposefully made our job a little harder by having the legs that have non-negligible mass and inertia, such as humans. And that was important for us because attributes such as the start initiation of the swing phase through propulsion of the thigh is something that depends on the inertia of the thigh. If your thigh is massless, you cannot do that. And for that, I refer to Daniel Ranievsky and I'll go for further discussion if you want. Or more importantly, perhaps, the energy that the shank takes from the gravity during the swing. So the shank can free swing in humans and harvest energy from the gravity. So again, if the shank doesn't have mass and inertia, it can't do that. So human-like walking, to a great extent, relies on the dynamic attributes of the limbs. So we designed the robot for maximum speed of 3 meters per second. So the actuators were carefully designed to provide the necessary torque and speed, both of them, for that. And the structure was also designed to withstand the forces. And getting to the main topic, it has highly vectorable actuators. Perhaps less than 2 Newton-meter. It's very easy to move the actuators around, which should be useful for the things that we try to accomplish. Also, to get advantage of this vectorability, one of the things that we did customize motor driver. So motor drivers usually have position mode, torque mode, and speed mode. So we add another mode to the driver, which is impedance mode. So we are doing impedance control on board in higher frequency to get better results. So the controller that we kind of are starting with is this force-based oscillation control. Again, in a lot of robots today, especially the ones that move more dynamically, you see this kind of stomping on the ground. And That is because of this force-based oscillation scheme. It's like a clock or time-based feed-forward input that leads to that stamping, and if you design it correctly, leads to very highly stable locomotion. Years ago, I did this at Oregon State on HES. Notice how it's stamping its legs on the ground, and it can blindly go over and come down from a pretty large obstacle. So this scheme is very useful because force oscillation is a very robust scheme, always converges to the same thing. I'll get back to this later. But the thing that this control relies on is the model is based on mass, spring, and damper. So the legs are spring and damper, and HES has physical springs, the linked springs that could satisfy the conditions of this model. So these actuators in the direction are the ones that cause that stamping on the ground of force bases. So another work that I did when I was at Bobby Gregg's lab was this back-drivable actuator that could do the open-loop impedance control very effectively. So as you see, I'm moving the actuator, the load cell that's measuring it, and here we compare the result that we get from the load cell from the response of a real mass spring damper if it was the case. So as you can see, the impedance control, open loop impedance control is perfect. The load cell is just measuring and verifying the concept. It's not a closed loop based on load cell. So it shows that if you have enough back drivability, you can do very good impedance control. So this one wasn't even onboard impedance control, it was offboard. And Mitra has back drivability even better than this prosthetic leg. So these videos show some of the examples of different parts of Mitra, how back drivable and low friction they are. Especially in the right video, as you see, the motor is off, and the knee can do very well the free swing, the same way that you see in humans. So that's something that is important for us. Perhaps even more interesting, my kind of favorite video of back drivability is this one. So this was a kind of old video, perhaps a little bit after last year's dynamic walking. We were testing the robot after finished building it, and we were testing the joints one by giving sinusoidal waves. And if you look at this, you just see that both legs are moving in opposite phases. And I kind of yelled at my grad student that I told you, test the joints first one by one. I thought that he was trying just to impress me or whatever. And he said that there's only one joint working. And then I noticed that the other one is just moving by the reaction torque of the other leg. So it's so back drivable that you hardly can notice which one is being actuated and which one is just moving passively. So back drivability is great. So we can do impedance control, and we should be able to do whatever we're trying to accomplish using that force-based oscillation scheme. Right? Right. So, first thing that we did, seriously, this thing happens. So, yeah, that was pretty spectacular. And if you want to see the zoomed out version, you see how the grad students freaked out. It's like this. Okay, so, thank you. It took us a while to figure out what's going on here. First, we suspected that because we were testing for a rather long time, the temperature has gone up, but then we investigated and saw that that wasn't the case. And finally, we found out that the regeneration current is actually much more than we expected. I had quite a few experiences with regeneration, and I've seen that because regeneration efficiency was always pretty low, a little bit of current goes back to battery or to other motors. But in our case, both because of very low friction and the pretty high inertia of the leg segments, even for small velocities, we get a lot of regeneration currents. So that leads us to a lot of safety features, adding it when we are stopping the leg so that the regeneration current doesn't go where it shouldn't go. And another thing that happened, kind of related to this, was that we started hitting the joint limits. So even though we had safeties that should have prevented the leg to hit the joint limits, we saw that they don't work very well. So again, we investigated and saw that what was happening was that we are commanding the current, but the measured current of the driver is much lower than that. And we realized that we forgot about this diamond plots, that we actually considered it very carefully in design for the gate cycles of maximum running speed that we were, it was our goal for. But in our safety region, safety module we didn't consider. So what does it say? It says that, for example, usually you see the maximum torque that is reported in datasheet is either this top of this diamond for this particular motor 30 newton-meter, or the maximum current that you can handle by your power electronics, or your demagnetization torque. But the thing is that your maximum current, maximum torque reduces by the speed of the motor. So if the speed is high, your maximum torque is low. So for example, for this red dot at 100 radian per second, or almost 1,000 RPM, which is a pretty normal speed for a motor, you only have about 10 newton meters, which is much lower than your peak torque. So what can we do to stop the motor from hitting the joints? My student tried to solve it by using some sort of MPC to predict what's going on in the future and embedding this relationship into MPC. But I philosophically don't like to just dump everything to MPC as it seems it's the case in these days. So that's another call, MPC calls. So we tried to look into the dynamics of the motor more closely and found that actually it was pretty easy. So if you have a motor with these parameters, your maximum torque, shown by this diamond, is either these lines or your Kt times Imax, which comes from the magnetization or maximum current, whichever is lower. And from the dynamics of the motor itself, you have something like this. So that I can be the average inertia that you have in that configuration from the limb added to the inertia, reflected inertia of the motor. So this is a linear differential equation. You can solve it and you get this exponential form for the omega s is where you switch from this limit to that limit. And you get something like this, so you can predict what will be going on if you apply your maximum available torque to the system, to the velocity of the motor. And then you can integrate it to get your theta, your angle, it should be far enough from your joint limits. So basically you see that at the point that you can make your omega 0, stopping the system, you should be still having some room from your joint limits. So that would be the condition when the safety module is activated and applies the maximum available torque. So, some margin from the joint limits. Alright, so it seems that these additional modules that we added to the safety of the robot is now getting the robot working better. So we return to that force-based oscillation scheme. So first thing that we are trying just recently was the control of vertical direction. So why vertical direction? Because I kind of believe that in walking, in locomotion, vertical direction, the direction of gravity is the most important one. And then again, why? If you write the dynamics of walking and approximate it the way that Geyer did it years ago by assuming small angles, which is a reasonable assumption for walking, not so much for running. You can see that you can write the dynamics of the system something like this. And what is interesting about this is that vertical direction will be independent of horizontal direction if your leg force is independent of horizontal direction. So if you design your leg force something like this, your vertical direction will have its own oscillation independent of whatever happens in horizontal plane, and its stability will trickle down to the horizontal plane built by the controller that you can add for the horizontal plane. So if you want to talk about in terms of Poincare map, the Jacobian of Poincare map will be diagonal, and the stability of the vertical direction and horizontal direction will be independent of each other, which makes it a very powerful paradigm. So that's why I'm saying that vertical direction is the most important direction for control of your robots. If you do it well in vertical direction, horizontal direction will be pretty much just foot placement. So we started making the robot control in the vertical direction, so that chain and the valve is purposefully short so that it doesn't drift apart. And as you see, it can stomp on the ground, and vertical leads to stable vertical oscillations, but the foot placement is a mess. That has a different reason, because we have issues right now for estimation of velocity of center of mass, which is not related to this controller. So hopefully we can fix that velocity of center of mass soon and can get the foot placement in order, and we'll get the robot to walk. In simulation it works well, because in simulation your estimation of center of mass is perfect. So, but in reality, I don't know why, the velocity of center of mass sometimes goes too high, so that these weird foot placements occur.
So much?
Yes.
How many more slides?
One.
Oh.
Okay. And to show that what's happening in the vertical direction, this is the ground reaction force of the two legs. So as you see, one leg has a smaller force than the other because the robot drifts to one way, so the chain kind of pulls the robot. But the other leg is pretty much doing it freely and taking all the mass of the robot, all the ground reaction force. And it's interesting that it's kind of double hump, which is the standard for spring mass walking, and as of now for also inverted pendulum, as Group has shown. So with this, I want to thank my students that have been working on this project in the past 2-3 years, and thank you. you also for listening.
What type of gearboxes are you using, and like what kind of gear ratio you're using? Just curious about how you got such good back drivability.
So for the ankle, for both of them, we are using planetary gearbox. For the ankle, single stage. For the rest, compound.
Okay.
And the gear ratio for the ankle is 7, but we have also some linkage that changes that gear ratio. It has some mechanical advantage. And for the rest, the gear ratio is 15:1. One thing that I forgot to mention, and thanks for reminding me, was that for the ankle inversion, the linkage actually reduces the gear ratio. So the inversion is much more back drivable than any other degree of freedom, because it's important just to adapt to the ground. So when we are hitting the ground, inversion is not doing any control. And because of its back drivability, just sits on the ground pretty much like what humans do. Yes?
So the diamond there, that's never the way that I've drawn the speed torque limit. I've always drawn it as lines continuing into the second and fourth quadrants.
Yes, that's the case if for the negative part, right? That's the case if you have a regenerative braking scheme. If you don't, it becomes like diamond like this. You cannot, your motor cannot apply extra current.
So that's a limit you put in the controller to keep it
on a field-oriented controller on the drive.
How about the backlash of the gear? If you are using planetary gears, you have a backlash usually, right?
Yes.
How is it? Is it good?
It's like an average planetary, so we live with that. Yes.
I would have a question for you. You have the very fast joint space or joint based impedance controls. Can you map this, or can you map a Cartesian impedance into this joint space locally or similarly? Can you do Cartesian?
Yeah, because you can command the impedance in each millisecond. So the driver is much faster than that. It's 8 to 10 kilohertz. So 8 to 10 times faster. But in each millisecond, you can also send command to the impedance controller, which can be coming from the Cartesian controller.
And the impedance controller is how fast? Like the joint space?
It's I think 8 or 10 kilohertz.
Thank you.
Yes.
You said that the vertical axis control is important and the horizontal is not that important.
It is important, but the vertical is more important because vertical is independent of horizontal, or you can make it independent of horizontal, but you cannot make horizontal control independent of vertical.
But if you have other segments like upper body, then there's a little bit different.
Well, we are talking about distributed order model. So when you
When
you have
you
other,
know what you have, you try to have also kind of human like design with the center of mass and everything, then you have also upper body.
yeah, that will be the next step. So because this controller has worked before and we were familiar with that, and it relied on the spring mass model, we tried to replicate it on this robot as proof of concept and as the first step. But you're right, in the next generations of controller, we need to add other features to it. Yes.
Siavash, I'd like to give you a summary if I can.
Please.
There's a cult that loves back drivability, but proponents may show some senility. Regen makes too much current, leaving drivers all burned. Fixing that limits later mobility.
Very nice.
Yeah. So I'll focus a bit on the forced oscillation part. I mean, I don't think it can be overstated how much that's influenced a lot of modern bipedal stability, these really dynamic bipeds. Where would you go next? Like, I mean, like, it does a lot, I imagine, but it does kind of limit what sort of footholds you can shoot for, and we can sort of, as humans, change our pace. What would you look for to maybe expand upon what you've done for more, maybe flexible mobility?
So the first thing that I want to look into is the effect of the ankle. This paradigm is relying on a point foot, right? So I want to see what happens if we add an ankle, if the same paradigm can be extended to a model with the ankle. So that's the first thing that I want to look into.
Thank you.
All right, thank you very much.